So, herzlich willkommen. So after we have looked at proposition logic and we have looked how we can solve proposition logic formulas by enumeration or by resolution, today we will start at looking at a combination which is called at the end what we will see the DPLL style SAT solving. So all SAT servers or most of the SAT servers that you can access that is available for usage that you can download in the internet will be based on this decision procedure. So let us start with what is our problem given proposition logic formula phi, and we assume from now on that the formulas are always in conjunctive normal form. We know already that each formula can be translated into CNF in linear time and space if you use the Zeithin transformation and take some additional variables for the encoding. And usually for the SAT solvers, the number of variables is not the big problem. So this cost of having new variables is not a serious disadvantage for solving satisfiability checking. Okay, and we would like to know if this CNF formula is satisfiable. That means if there is a model for it, an assignment to the variables such that the formula becomes true. There are three main components in SAT solving. This is decision, Boolean constraint propagation, and conflict resolution and backtracking. We look at them one after the other. So let us start with decision. Here we have a very simple formula in CNF with just three variables. And if you look at the state space which we want to search for, of course we can make also a truth table, but we can also look at the state space like a binary decision diagram. That means you have nodes with the variable names and the decision whether the value of this variable should be 1 or 0. So for example, the assignment where all three variables get the value true is this path. And the question is, if there is a leaf with the entry 1, this would correspond to a satisfying assignment, and if in the leaf we write a 0, this means it is an unsatisfiable path. So now the basic decision, I just draw one tree here, but I already made a decision, namely that I take a certain variable order to consider the assignments. I took first x, and then if x is true, I took y, and if x is false, I also took y. This means static. That means independent of the previous assignment, I will take the same next variable. And I give an order on the variables x less than y less than z. That means x comes first and z comes last. Last week you have already seen that this variable order and also the sign assignment can play a very important role in the efficiency. That means if I have one variable order and another one and try to solve with both, then one can be very fast and the other one can be very slow. So let us now look if I take this x, y, z and I take the decision that if I search for passes in this tree, then I always go first the true path. And this is visualized by the fact that true is on the left. So I draw these trees such that I always go the left hand side first, and if it does not work, then I go to the right. So what would we do with this decision heuristic? Let's assume first I tried really all complete assignment one after the other. So I would go for the left first, and I would arrive in this leaf. And what would be the entry in this leaf? Is this assignment satisfiable? If all three are true? No? The next one, I would now go the other path. So, is that satisfiable? Also not. Then I would now backtrack to this node and go the other side and then always to the left. This is also not. And what is without the next one? then I would just now arrive here at x and go the false part. What is with this one? Okay, so we have a solution in the 5th try. Now just for we can look at how important the order can be now. The only difference here is I change the variable order. So what is now, if I start, I always go to the left, but now I start with Z, and I still take first the positive variation. So this I go first. This was the same as before. Every variable is true, so this was false. What is with the next one? Is the second one satisfiable? Yes. So you see, instead of 5, we have now the second one. Let us try one more. Now the difference is I have x first, but I take first the negative values. So that means now I have 0 on the left, always. So what is the first one? Okay. So this was better because I found already the first time. And just the last combination, now I again turned around. So Z is the most, the first one to assign, and all are negative. So what is with this one? It's also satisfiable. So you can see that depending on the variable order and the choice of sign, which I try first, of course I can be more efficient or less efficient, depending on if I have the luck to find the true passes first or not. So do you think that there is an optimal strategy for variable assignments? That means, can I somehow choose a heuristic or a strategy that I always find the true leaves first? Now there is a native one, namely I could solve the problem and then choose the true path first. But this is the basic point, that choosing the right decision heuristics to find the right one, the optimal one, is as hard as solving the problem itself. So it doesn't help us much. But there are heuristics which help us to find, to increase the probability to find satisfiable solutions first. And the basic reason for that is that the problems we normally solve are not just randomly generated, but they correspond to some physical systems and some properties of these systems. And due to this fact, there are some heuristics we will see later, which help us really a lot to speed up the search. But for the moment, we only see that it is very important how we choose this. Now, we look at two decision heuristics that were used, or that are used in some solvers, and we'll come to a third one, which is used in the most solvers nowadays last. So the dynamic largest individual sum, DLIS, is tries to find satisfying solution first. So we have two possibilities, but basically we do not know if our formula is satisfiable or not. If it is satisfiable, then it is perhaps a good choice to search for satisfiable passes first. If it is unsatisfiable, then it would be much better to try to run into subtrees where we know already at a relative high point that the whole subtree is unsatisfiable. We will look at it later. But this dynamic largest individual sum tries to find satisfying passes first. That means it tries to satisfy with each assignment as many clauses as possible. How does it do that? Assume we have for each variable we count the number of clauses which are not true yet. That means no variable yet is assigned such that the literal in the clause became true. And I count these clauses, unresolved clauses we call them, which are not yet true, in which x appears positively. This is stored in the variable cxp, p for positive. And I count also the number of clauses in which x appears negatively, that means negated, and this clause is not yet satisfied. I do this for all variables, and then I choose the maximum. That means I choose the maximal positive, the maximal negative value, and I take the larger of them. If the positive one is larger, then I take x. If xp is the largest, I take x and assign it true. And if the negative one, the maximum is in a negative path, then I take the variable and assign false to it. Now, we can see that this is in efficiency. For each decision, I have to count through the literals. And it is linear, as you can see, because, of course, I want to assign a variable. In order to assign it, I only have to look at each clause once. So you can say the efficiency is linear, and this is great, because only exponential is very bad. We could still live with polynomial. This is the usual experience that we make with complexity. But the problem is that these decisions are made really a very huge number of times. And in practical examples, you have a huge number of clauses. So typical industrial applications have at least some 100,000 clauses with some 10,000 or so variables. And you will have millions of assignments, such decisions. So it is very expensive, and that's why it does not work always well in practice. But in theory, we can look at our example. If we have C1, C2, C3, and let's say we take this dynamic DLIS variable order. That means we have three variables, and we compute what is the value of, in how many clauses does x appears positively, which are not yet true, negatively. The same for p, for y, and the same for z. Oh, sorry, this is negative. So, what is CXP? In how many clauses is x? In how many not yet true clauses do x appear? None? In negatively? Y positively, we have one, no? Two. Mm-hmm. And Y negatively? Z positively? And Z negatively? 1. Okay. So, and we take, if we have equal values, we take the first one. So the first one would mean 2 is the largest value and xn is the first one in the order. So I would take x, and first I take the negative value. And now x became negative, and this is the problem. I have to update the list. Since x negative satisfies now C1 and C2, so these literals I have to remove. That means x positive is still 0, but x negative is now also 0. Because where x appears negatively, these clauses are not true. Y appears positively in 2 clauses, but in C1, this literal is already true. So these true are not true. So that means only C2 is not yet satisfied. That's why only CP becomes 1, Cn is also 0, and Zp is 0, and Zn is 1. So now 1 is the largest value, and I take the first one, so I will take y. And I take, because Cp is the larger value, I take now the positive part. And now I have to update the list again. So, positively, yeah. So now I have to update the list. And this will mean the C2 is also updated, yeah. That means I have actually no unsatisfied clause. C1 and C3 are satisfied by the negative value of x and C2 by the positive value of y. So I know that both, I know that both of these are satisfying. Sorry, this was the wrong place. And if I would have found out that these are not yet satisfying, then I would have tried 0 for y. If I take 0 for y, then the only clause unsatisfied is still C2, because x is false. So I would take now set mid false. Yeah, because this would be the only unassigned variable with a non-zero value, and this satisfies. So if all three are false, then all clauses are satisfied. And if you can remember, this formula has 3 solutions, so we have all 3. That means all the rest will be 0. I just write now. Every path on the right will lead to 0. And this shows that this heuristic is efficient. That means we found a variable order with which we found the first 3 passes, the satisfying ones. And which we would found later, they are the unsatisfying ones. So this is what we want. But you have also seen that we have to compute quite a lot of this update, the activity values of these numbers of appearance in unsatisfied clauses. And that's why this is not so good. So there was also a try to find something, okay, this is just the same that we draw more in a nicer way. There is another method, this is static. This is the Jersolow-Wang method. And this also tries to, not to find satisfying solutions first, but try to find either solutions fast or conflicts fast. And we will see later why it works good. The basic idea is that it tries to take variables which appear in short clauses, either in many clauses or in short clauses. Why it is good if it appears in many clauses, this you can already think. If it appears in many clauses, it means that it has a lot of influence to other variables. That means either it satisfies a lot of clauses if I take the right sign, or if it becomes false, then the other literals must be satisfied. So kind of it implies that the rest of the clause must be satisfied. But these long clauses are, if a clause has a lot of literals, then it takes very long till I can conclude something. So it says, okay, I add up the negatively weighted lengths of the clauses, and this negatively weighted means 2 to the minus, this is the length of the clause, the number of literals in the clause. And that means if there are a lot of clauses, then this sum can get larger. But if the clauses are long, then the weight gets exponentially smaller. So let us again look at our example. So we have again value for each literal. J of set and not set. So what is the value of J of x? I just go back. So now we have here x as literal, and we add up 2 to the minus length of the clause for all clauses in which x appears. So what is the value of J of x? In which clauses does it appear? In 0 clauses, so I add this sum is empty. What about not x? Yeah, C1 and C3. C1 has 3 literals, C3 has 2. So 1/8 plus 1/4. What about y? Now y appears only in C2. It has 2 literals. Oh, C1, very good. So it is the same as on the left. One clause with 3 literals, C1, and one clause with 2 literals, C2. And not y appears only in C3. Set is only in C1. And not set in C2. So we get an order. The highest values have not x and y. And again, if we, under the equal values, we take the order of appearance, then not x, then y. But the next value is not y and not z. Then the smallest one is z before x, which does not appear at all. So if we now get the tree, I start with x and I take first the negative value. Then I take y. First take the positive value. Then I take z. First take the negative value. And is this solution satisfiable? Mm-hmm.
Doesn't this have a higher value than not y?
Sorry?
Doesn't this have a higher value than not y?
Z. Now 2 to the minus 2 is 1/4. 2 to the minus 3 is 1/8.
Yeah, but isn't exactly the other way?
So this here is 1/4. This here is 1/8. This is 1/4. And the other values are larger. Hmm?
So we maybe should y to not y. Not go to z, but to go to y from y.
From y to the 0 value?
Actually, we've got so we choose the value 0.
Mm-hmm.
Then for y, we've got the positive.
Mm-hmm.
And then we should choose negative value for y again.
No. Y has already a value. So the next decision I can take only something which is not yet. So if I take on one path y and not y, then it is not an assignment. Yeah. So these are just, this means actually that y is higher than not y. That if I may choose, then I will always take y. Yeah. So this is a kind of not x, y, and not z. Okay, so then I take false for z, and is this a satisfying solution? Yeah? Okay. If it wouldn't have been, what is about this one? This would be the next to check. Any? Yeah? Okay, if it wouldn't have been, then now I would have again y is false, but then I take the next unassigned in the list and this would be set with false. And what is the value of this? Is 1. That means again with this method also we have found the 3 satisfying solutions first. Here it is again in a nicer way. Okay, these methods basically work, so the first one works well, but it is very expensive. And this second one, the problem is it is static. That means now for this small example it works well, but it would be also much better to compute it dynamically, because this way this counts the clauses at the beginning, but then I assign values, so the satisfied clauses will not be considered in this sum. And also, if I already assigned false litters in a clause, some litters are false, then the remaining ones which are unassigned are fewer. So actually, this clause should have now a larger weight. Yeah, because the number of litters in the clause is actually smaller if I already have assigned some. And in the static way, this since it does not consider these points, it does not always work well. Okay, we will see one more later. But for that, we have to look first at 2 things. First, the Boolean constraint propagation, called shortened BCP. Let us come back to our example again. And assume we have the variable order x, y, z, and first we assign positive litters. So what I would do is I go first this path. This is the first to check, and then I recognize, as we have seen, that this is unsatisfiable. And now, in a naive way, I would go now this second path and check, and this would also be unsatisfiable. But could I do something better? I mean, what is the reason that both of these passes do not satisfy my formula? Yeah, that's true, that we have also seen in the other assignments, but once I branch to x1, what happens then? So I state that I do not have to look at both of these.
After I check the first time, I see that the first clause causes the problem unsatisfied. So maybe I should try find a certain solution for the third clause.
Okay, this is a good idea. So let's say I take now the third clause and I know x and y together cannot be satisfied. So if x is true, then y cannot be true. This path I shouldn't go because of C3. And this would tell me if once I assign true to x, I have to assign false to y. Otherwise it doesn't, the formula cannot be satisfied anymore. I can take the same for the other one. So C1 says either x is false, that means if x is true, it can go wrong. If y is false, it can go wrong. And then set also false. This one, yeah, this is C1. And C2 would say if y is false and set is true. y is false and z is true. Yeah, so each clause cuts a kind of subtrees away, which I do not have to look through. So once I recognize that in a clause all but one literals are false, then I know I have to make the last literal true, otherwise the clause will become false and the whole formula is unsatisfiable. And that's why the solver takes CNF as input. So I can look clause by clause and they are independent. Every clause must be satisfied. So from each clause I can make some implications. Given a partial assignment, it implies some new assignments. So actually I would not even come into this subtree. If I assign true to x, then it would imply that y must be false. And what happens then? So now I assign true to x, then due to C3, y must be false, and then what happens then? What will be implied? I'm here, and I said by each clause, if it implies, that means all literals but one are false, then I take the search into the subtree satisfying the clause. So what is the case here? I have two clauses, C2 and C1, and they tell me the opposite. What does it mean for my current solution? That I'm in an unsatisfiable subtree, because I can satisfy only one of them but not both. That means I do not need to go in this subtree, not in this. So I will go back and continue here. And if I take always the last one, I will end up here. And if x is false, then C1 and C2 are satisfied. If y is true, C2, so this will be a satisfying one. And then I'm done. So now we have still one problem, namely, first I wanted to show something else. Here you see I have a static variable order, and this is kind of seems to be reflected in this decision tree, that always first x, then y, and then z. But even if the variable order is static, if I consider these implications of the clauses, then this tree becomes dynamic. So if we add up a last clause, then we can see. Assume now still x, y, z is the order, and we first take positive values. So I take x with a true value first. What happens then? These two literals becomes false. These three. And then my next literal in the order would be y, but we can already see here in this clause that to satisfy it, z must be true. So in this case, I add up z here and say I take it first with value true. If z is true, then not z will be false, so it will imply that y must be true. And now if y is true, actually the order is also important, but nevertheless, if y is true, then I see here this C3 is not satisfied, so it is 0. And if y is false, then C2. So I must try another value for z. If z is false, then I have a problem with the C4. But now I see it earlier. So probably the value of x must be different. Now I try false. So this clause is satisfied, this clause is satisfied. And then only C2 not. Now nothing is implied. So now I take the next one in the variable order. It is y. And I say that first positive value, so I will take here the 1. And the clause is now already satisfied, but I will go on in the variable order. I will take set, also with true value, and then I will see that this is satisfying. If I want only one assignment, I would stop there. So, and why I showed this extension, because you see in the left subtree of X, the next node is Z. And in the right subtree of X, the next node is Y. So that's why we have a static variable order, but the variable order for searching for assignments is dynamic. Because first I always assign a variable, and then I check what is implied. And only if nothing else is implied, if I cannot deduce any further implications, then I take the next one in the variable order. Good. Now let us formalize it a bit. Now we can see that a clause can change its status during variable assignments. Namely, first, it is unsatisfied if it is not empty. Because there is no true literal in it yet, but it still has literals which are unassigned. And then during assignment, either a clause can get satisfied, that means it becomes a true literal, or one of its literals becomes true, or it gets unit. These are the implying clauses, that means all literals are false but one, and then this last one is implied to be true. Or it is unresolved, that means it is not yet true, but there are still more than one literals which are unassigned. Here you see some examples. So if I have a clause x1 or x2 or x3, then this clause would be satisfied. 1 means true, 0 means false, and nothing means unassigned. So we have a true literal here, a false one, this is satisfied. If all are false, it is unsatisfied. If 2 false and 1 unassigned, then it is unit. This last one must be true. And if I may have some unassigned ones, some false ones, but not true yet, and at least 2 unassigned, and it is unresolved. And the unit clauses are those which are important for this so-called Boolean constraint propagation which we looked at. But now we have still one problem, namely we had looked at this implication by looking at the trees representing the search space. And the efficiency of such solving is that it does not need much space. That means it will never build up this search tree explicitly. This is what is done by model checking. That the whole search tree is built efficiently. It can be also built symbolically, but nevertheless we have the state explosion problem. That means model checking would indeed build these trees that we have drawn and would check them for emptiness. That means if they have a one leaf or not, whether they have a one leaf or not. And such solving is just the other round. So model checking is efficient in time, or it is faster than such solving, but it needs much more space, much more memory. And such solving does not need much memory, but it goes a depth first search, if you like. So it will never build up this tree, but go each pass implicitly in this tree. That means it puts the same effort in time. So if you have a larger problem which is not solvable due to space by model checking, then you can take such solving. Perhaps it will take longer, but if you wait long enough, then you can still do it. So we do not have this tree, and we cannot remember these implications. Or if we do not remember these implications, then we do not know where we are. So if I go back to this example, assume that I don't have this tree. The only thing what I do is I remember, okay, I have now X, and then I have Z, and then I have Y, and then this was unsatisfiable. So where to continue? So this looks like X. If I don't have this tree and know I am now in this leaf, then I don't know how to continue. X set Y, it can be that I have to flip Y, can be that I have to flip Z or X. And besides that, I do not know if the other value was already tried or not. So I need a kind of, first, remembering the implication, and second, remembering what I have tried out and what not. And this I do by adding some clauses later, which are generated according to an implication graph. The implication graph is nothing else than remembering where I am in my tree, especially which decisions were real decisions and which assignments were just implications of decisions. So I remember a graph which whose nodes correspond to variable assignments, and I count the decisions. So first I assign a variable at decision level, let's say 1. Then I make implications, and all implications I count to this decision level because they are consequences of the first decision. Then if there are no implications anymore, then I take the second level, decision level 2. Then I also check what is implied. So decision level 1, then I have a decision variable, and this may imply several others. They are all at decision level 1. Then we will have decision level 2. I take a variable, it implies some, perhaps also with the help of the variables from the previous level, and so on. So this is the decision level, and we use this notation. The variable x has value v, and this was assigned at decision level d. So we had this example, and now instead of the tree, we draw the decision tree. So we said we start with x. This is done at decision level 1. Then if x is true, this will imply by C3. There I can make x is true at decision level 1. And by C3, this implies that y is false also at decision level 1. So now x is true, y is false, that means these literals are also false, and this will imply by clause 1 that Z must false. And now we have a problem with clause 2, which says that these two values are conflicting. Yeah, this is an implication graph where we have special notation for decisions. We distinguish them from the other ones, other nodes which are implications. So if you formalize it, an implication graph is a labeled, directed, acyclic graph. Yeah, labeled means I have here the clauses which implied this assignment. It is directed because the implications are directed. One assignment implies another one, or also several assignments, like in the case of C1. The literals which were false, these two, together imply one assignment. And of course it is acyclic, because if a variable is assigned, then I cannot assign it again. So I cannot come to cycles. And the graph has a set of nodes. These represent the literals of the current partial assignment. And each node is labeled with the literal, which is true, and the decision level at which the assignment was made, and the set of edges are those pairs of nodes which Vj is assigned, and its assignment is due to a clause, this is called antecedent, in which not Vi is included. That means not Vi was false, and that's why Vi that implies, which is true, implies that Vj must hold, together with the rest, remaining literals. Okay, and we can also have a special node. This is a conflict node. This we had here with kappa or k. And its incoming edges belong to the clause or come from the literals that build a clause which is false under the current assignment. So here, for example, C2, these two literals together build C2, which are both false. That means that we have a conflict. Okay, and again, this implication tree corresponds, if I now show it again, x is 1, then I take false for y, and then I take true to z, and I am at 0. But whereas in the tree, I see which parts I already had and which not, because I always make left first. In the formula, I don't see. That's why I need this implication graph to see which path in the tree I have taken. Okay, so we now have at least partial assignment and have an implication graph. Here I have one more example. So assume we have these 6 clauses. And now I try first to assign x7. This becomes false at decision level 1. There I always start. And it does not imply anything because x7 appears only here. So this became now false, but it doesn't matter because there are still 2 unassigned literals in the clause. Then I assign at decision level 2 x8. So this becomes also false, but it doesn't imply yet anything. Then at decision level 3, I assign x9 false. So now these 3 are false, but no implications yet. But this changes now if we assign true to x1 at decision level 4. What happens now? So these were already false, and now also these 2 literals are false. So what will be implied? By clause 1. So unfortunately it's always removed. So now x2 is true. And this is true. So the next one, x3 must be true by the second clause. So x1 was false, x7 was false, so x3 must hold. The next one, what is about the third clause? Okay, x4 must be 1 because not x2 and not x3 are both false. So now x4 is true. What is about the fourth clause? Now x5, the next one. Yeah, 6, and one more. what is it, the last clause? It's unsatisfied. That means it's a conflict. In the last clause now I have not x5, not x6, but x5 is true and x6 is also true. So it is a conflict. That means I made here 4 decisions, and these 4 decisions together implied that my formula is unsatisfiable. So now what we did until now is first we talked about how to choose a variable and assign a sign to it. Then we looked at, to shorten what we have to look through, we can do implications, and we can only follow those solutions which do not contradict these implications. And as we see, sometimes nevertheless we do not succeed, so we end up in a conflict, and then we have to change something. So what would you change in this case? How would you continue the search? At decision level 1, you had not x7, then at 2 you have not x8, then at 3 you had not x9, and at 4 you had x1. So what would you do now? What would be the most natural? Obviously, this combination of these 4, if I take these decisions outside, then they will always lead to this conflict. Yeah? So this combination I don't need to try anymore. What could we do next? Exactly. X1 would be the native choice because we will not store it as a graph but in a list, the implications. We say variable, for example, x1, what is true with this reason. And then the next, so it will be an array. This will be the first entry, this will be the second entry, this is the third, this is the fourth, this is the fifth, and so on. And this already encodes the whole tree. Yeah, I do not need more information. So then I only have to pop the last elements from the list or from the stack as you see. So we could flip this value, and now I could try x1 false. Now assume I build up a new tree, x1 is false, and I get again a conflict. How do I know that x1 true was already tried? How could I reach that I do not go again into the same? Otherwise I would always flip the last, and then it would never terminate. Could I make a trick that assures that I do not try this combination anymore? Now, obviously, we have to remember it somehow. What would be the more native way to remember? Not this combination. So I should take either not x7, either x7 or x9 or x8 or not x1. Yeah, this means do not take the same combination. One of them should have a different sign. So, and how could I assure that I do not make this again? No, just put it to your closed set. Yeah, I had until now, I had 6 clauses, and now I introduced the 7th one. I put it to my closed set, and then, so this clause is now false. What would I do then? somehow I must resolve this conflict. So obviously I have to undo some assignments. I would undo the last decision level, the 4. That means I would come back to here, but now I have a new clause. And now, at the 3rd decision level, since all 3 literals are false, it will imply that x1 must be false. So I would have here now x1 is false at decision level 3. I shortened down the path. And this corresponds to, if you look at the tree what we had before. So x7 we tried first false, then we tried 8 false, then we tried 9 false, then we had x1 true. This led to a 0 leaf with some other implications. And now we say, okay, once you go this way, then go directly the 0 leaf. And we are at this point now. Is it clear? Yes. Okay. So what we have now is that we assign variables, store them in a stack or in an array with the information if they are, whether they are decision variables, and if not, which clauses implied them. Then, of course, if I find a solution, I'm fine. If not, then I have a conflict. And then I can say this combination of decisions should not be considered in the future. I do this by learning a new clause, which is, say, not this combination again. And then I continue. I undo the last decision, and this clause will imply at the second last decision level that I should flip my assignment. So this would say already at the third, here. And to the, this is called Boolean constraint propagation. One last thing. We said that each time I assign a variable, I check if there is a unit clause. That means one clause where all literals are false but one, which is unassigned. Or also if all are false because this is a conflicting clause. But to do this, I should check all clauses after each assignment. And this would be very inefficient. So is there a better way to do that? I have a set of clauses. I assign a variable. At which clauses do I have to look? I do not have to look at all, obviously, or in worst case at all, but in general not at all. How could I speed up this implication, this propagation? Perhaps by storing some information about my clause set. Any ideas? Now let us go back here. Perhaps to the smaller example here. First I assigned true to x. Okay, I remove this. Okay, I assigned true to x, and now I would like to propagate. In which clauses may something happen, and in which clauses not? So I go now this way. I'm here. Sorry. Yeah. Not yet there, here. I assign true to X. In which clauses can something happen? Can in C2 something happen? Can there be an implication? Of course not, because X does not appear in C2. And also, if in a clause X would appear positively, there would be no way of any implication because this clause becomes true by this assignment. So only those clauses which have not X as literal could imply something. They could become unit, basically. Okay, what is the solution? I just store this information. Store for each literal a list of clauses in which this literal appears. If this literal becomes false, then you have only to look at the clauses in the list. Sounds easy and natural, but there is one problem with it. These clauses which we look at, this change, because with each conflict we learn a new clause. So we will extend the lists for the literals of the newly learned clause. This is not yet the problem. Extending lists is fine. We just append an element at the end. The problem is that these clauses also get deleted sometimes. We say we do not only learn, we also forget. The reason for this we will see later. That means sometimes I also remove clauses. And then I have to search in the list. So if this clause has literals L1 to Ln, then I have to search in n lists for this clause Ci. I have to remove it. Searching is inefficient and removing is also not so efficient, depending on the data structure. So if it is an array, then all the elements afterwards you have to push one back. If it is a connected list, then it might be more efficient to remove, but then the access is not so efficient. So that's why this already speeds up a lot, but it is still unsatisfactory to store the lists of clauses in which the literals appear. So what else can we do? So we could keep for each literal a list of clauses in which it occurs. What happens now to these clauses? They have literals L1, L2, L3, L4, and so on to Ln. They are first all unassigned. And what happens then? The sum may become true, then the clause is satisfied. So if one is true, then we are done. If none of them is true, then at which point can this clause imply something? How many literals must become false to imply? N minus 1. So only one is unassigned. Only then it can imply. But as long as two are unassigned, it cannot imply anything. So what is used usually is the so-called watch literal scheme. That means we take only two literals and we keep the lists for these two literals of clauses in which these literals are watches. That means in each clause, if I go back here, I can choose two literals. These are usually the first two in the clause, if it is stored, such that we do not have to remember the watches. If I store a clause, just the first two literals are watches. That means if one of them is true, it's fine. And if both are unassigned, it's also fine. It should not be the case that one of them is false and the other one is not true. And if this holds, then this clause never implies. So I will store in the list of L1 that this Ci is L1 is literal for watch literal for Ci, And for L2, I will also store that CI, in CI L2 is a watch literal. And what happens now, if one of them becomes true, let's say L1 becomes true, what do I have to do? Nothing. This will not imply anything. The clause became true, so I can let the literals as they are. What happens if one of them becomes false? Let's say L2 becomes false. Now my assumption is not necessarily satisfied that there are two unassigned literals. I had two before L2 became false, but now is L2 false, so this is not more suited for a watch. What do I have to do? Now I can check. Either is L1 already true, then I'm fine. Then I can keep L1 and L2 still as watches because the clause is satisfied. But if L1 is not true, then I try to search another position for the second watch. So I move this, let's say, to S3. If it is not false, I can take it. If S3 is also not suited because it is false, then I try S4. And so on till Ln. I try to search for one which is either true or unassigned. If I succeed, then it is fine. I have again two watches which assure that this clause cannot imply anything. And if I do not find any, then, so L1 is not true, and L2 was the watch, it became false, and I try L3, L4, and so Ln, and all of them are false, then what happens then? Exactly, true. Yeah. So L1 is then the last hope to satisfy the clause, and then it will be implied. So if I do not find a new position for the watch, then the clause is either unit and implying or conflicting. And this spares a lot of work because I do not have to check if one literal becomes false. I do not have to check it for all literals, but only for the two ones which are watched. So again, what we do is we take two literals in each clause which are either true or unassigned. And if one of these watch literals gets true, if one of the literals gets true, then we check each clause in which the negation is a watch, that means which became now false, then we check if the watch is true, the other watch, then the clause is satisfied, and if the other watch is not true, then we try to find a new position. If we find one, a new position which is true or unassigned, then we are done. Otherwise, we have the possibility either the other watch is false, then we have a conflict, or the other watch is unassigned, and then we have an implication. Okay. So now we have two of the components. First, the decision, how we can try to find optimal decision heuristics to assign variables and to choose their values. And then we looked at Boolean constraint propagation, which tells me that if I assign a variable, then before assigning a next one, I first check which assignments are implied by my decision, not to run into conflicts or unsatisfiable subtrees so often. But now the question still remains, if we have an implication queue or an assignment set, and this leads to a conflict, then how to continue? We said, well, we can exclude the set of decisions that at least we have to flip one. And this can be done, this is okay, but it is not efficient because several of these decisions perhaps will not have anything with your conflict. So let us look if we can do it a bit better. Here, this example which we had, we said we will exclude these four, the combination of these four. And then if we learn this clause, then we can be sure that we will never go into the same conflict again. But in this case, we would undo only the last decision level, and we will propagate this new information at decision level 3. That would mean that we would have a new assignment, and we would propagate this new assignment again. So the general rule would be to backtrack to the second last decision, and then propagating this newly learned clause, and you get some new assignments which you again propagate and so on. But if you look in this implication tree, you can see that we had this cut number 1, the outside. And now what would happen if we would take the cut number 2, this is here. What a cut means a line which cuts the conflict away from the decision. Yeah, so for example, this is a cut because from all decisions I have to go through this line to the conflict. Yeah, whereas for example, this one would not be a cut. Yeah, because it does not separate the conflict from the decision. Actually, if I make this cut number 2, then what is different from cut number 1 is that this here is not a decision. But this node is implied by these decisions, these two. That means even if I do not make these decisions, if I would assign true to x4, this would also lead to a conflict. Yeah, never mind if the value of true for x4 is implied or if it's decided. How it is assigned, it doesn't matter. This combination, x8 is false, x4 is true, and x9 is false, will always lead to conflict. Due to the clauses C4, C5, and C6. I can do the same implication. The same holds also for line 3. If I would cut line 3, this is also a cut, and it would tell me that x8 is false, x2 is true, x3 is true, and x9 is false. Together will always lead to a conflict. And so my implication tree stores my implications, but actually it tells me more. It tells me a lot of possible combinations of assignments which would lead to the same conflict here. So perhaps I can do it better than taking just the decision. First of all, because the number of literals in the clauses, so the number of nodes on the left-hand side or the decision side of the cut can be different. So I can have smaller or larger clauses. But more importantly, the involved decision levels might be different. And there is one more important thing, namely if I take this cut number 2, what we observe is that here I have 3 literals, which combination I would exclude, one at decision level 2, one at decision level 3, and one at decision level 4. So if I now would like to change something, I would undo the last one. I would undo decision level 4. And what I have is that at decision level 3, this clause will imply, to say it is an asserting clause. It will imply that I have to switch x4 to false. In contrast, if I would take cut number 2, this would have two litters at decision level 4. If I undo level 4, then this clause will not imply anything. This is not asserting. It gives me a piece of new information, but at that moment I cannot make use of it. So it would not directly lead to flipping the value. And if I take the decisions, it's always secure, but you see that here I may have a clause with 3 litters, and here I have a clause with 4, and also the generation of the clause going back, actually I end up in a conflict, and I have only this stack of implications, so I will go backwards in this implication graph in order to generate this cut. We will see later how it can be done. So the nearer to the conflict, the better, and the smaller, the better, and it should be asserting. It should contain only 1 literal at the last decision level. Then I can make the best use of it. Then it is cheap to generate, and it will give me immediately after undoing the last level, or some levels, some new piece of information and the new implication. So we can say what we want to have here is shorter ones are always better, but the inference on the backtracking level is the most important thing. It should be asserting, and it should imply that one decision will be, or at least one assignment will be flipped. And this is by taking an asserting clause that what has only a single literal at the last decision level, and then if we undo the last level, then it will become a unit clause. That means, this is what I already said, that it will force an immediate change from the current subtree. It will redirect the search into another subtree. Okay, and the fact of being an asserting clause, as we said, means that there is only 1 literal at the last decision level. And this means especially that all passes from the last decision to the conflict go through this node. This is a definition of the unique implication point. So you see here, this one in the middle is a UIP, unique implication point, because all passes from the last decision, never mind if I go this way or this way, everything goes from the last decision to the conflict through this point. And of course, the last decision itself is also a unique implication point, because every path from this node to the conflict goes through this node, but the distance to the conflict is different. And to distinguish the nearest one, we say this is the first unique implication point. So this is the first one, and the decision is not the first one, but it is also one. And now this means that we would like to have a cut which cuts the first unique implication point. That means for this we would have this cut, and for the decision as we had before we would have this cut. And we will always take the first one because this is the cheapest to generate. So the rule is we search in this implication graph by going backward from the conflict the first unique implication point. We will have a look at how we can do this, but basically it is moving the cut from the conflict. I go back. So at the beginning we will be here. So we have clause 6 is basically represented by this initial cut. You already know that this is false. I take the last implication, this is this, and take it to the other side of the cut. So now I have 1, 2 still assignments which are on the last decision level. Yeah, this one and this one. So I again take the last one. This is this node. So now I take it into the cut, And now I have only one literal at the last level, and I have it asserting close. Yeah, so this way I can always take one more, and then I will find the first one if I make it in backward chronological order of the assignment. And then now I have a close. If I undo everything to the second largest level in the close. So again, back to the example. Now I would undo the last level. And now, since I have now these 3 assignments left, everything else is undone, my new close will imply that this node will become a different value. Yeah? So I will backtrack to the second largest level. The largest one was undone. These are the black crosses. And then I undo everything to the second largest one, where these 3 still hold, and they will imply the fourth one to flip the unique implication point. Okay, so the general rule is backtrack to the second highest decision level, but do not erase it. Then our asserting clause will imply that the last literal, which was just undone, will become true, and we can assign it. So I said that we undo the last decision, at least, and we undo everything to the second largest decision level. Now, the question can arise, what is if there is no second largest decision level? Because everything was happening on decision level 1, let's say. Or also at decision level n, but all the cuts led to a close, which I learned, which has only, let's say, 1 literal at the last level. Where to backtrack then? So we can perhaps go. Let's say we have a x or y and not x or and x or not y. So I will try to make a decision level 1 not x. This is close C1, this is close C2. Will imply by C1 that y must hold, and these two by C2 will lead to a conflict. So now I make my cuts. The first cut is directly by the conflict. That means C2 is unsatisfied. But I still have 2 literals on the last level. So I will extend the cut here. And then I have a unique implication point and get the information that this combination should not happen, so x must hold. Yeah? But this is at decision level 1. So there is no second largest. Where to backtrack now? What shall I do? I am at decision level 1. I made a decision, and this implied a conflict without involving any other decision levels. Okay, we said undo the last level. Okay, I undo decision level 1. And what shall I do then? Shall I assign x at decision level 1? Yeah, the problem is I even do not need to learn these clauses. It works also if I do not learn them. And if I do it at decision level 1, the problem is at some point perhaps I get a conflict. I undo decision level 1 and I will flip it again. Yeah, this could happen. That also x will lead to a conflict. And if I make it at decision level 1, this means it is a choice. By assigning the value true to x, is it a choice? Is it a decision now, after this analysis of the conflict? Can it be that I find some solution where x is false? Is there any solution with x equals false? Yeah, again, these are my two clauses, only two clauses. Is there any solution if x is false? No. That means now I tried out x false and I recognize by implications that it cannot lead to a solution. I know now that x cannot be false. So if I do that at decision level 1, this would mean it is just a choice. Yeah, it is a decision, but it is not. I know that x must be true in order to satisfy my formula. So decision level 1 is not very suited. What shall we take instead? Yeah, we take decision level 0. Yeah, then we say we backtrack to decision level 0. We will assign x to true at decision level 0. And 0 means it must be this way. It is not a decision. It is something which is necessary to satisfy the formula. And just the last question before we finish for today. I just look. Yeah, I have one more slide. What happens if I now assign something at decision level 0 and propagate it, so I get new implications, and then I get the conflict? Exactly, because the facts, which are not decisions anymore, they must be, so imply a conflict, then I cannot resolve it anymore. Okay. So now we have seen all three components, and they can be put together to a SAT algorithm like the following. We always make a decision, and this decision just chooses the next variable and its sign. And if all variables are already assigned, that means we have a solution. Now, we have an assignment, so we propagate it. And if no conflict happens, then it returns true. If a conflict happens, then it returns false. And if there is a conflict, then we resolve it. We resolve it by this implication graph generating the first implication point cut. We learn this clause, backtrack to the second highest decision level, where this clause is unit, makes an implication, which is again propagated, may again lead to a conflict, and so on. That's why this while loop. So we finish there today, and on Thursday I'm not there, but there will be an exercise, and Nils will make the lecture. You will look at the Minisat solver without looking at the inside, just looking how is the syntax, which outputs are there, and play a bit around with that. So Nils will show it to you. And next week we will first look how this conflict resolution can be done efficiently, because we do not have this implication graph. So thank you.